Hello, in this section we look at 4.5, the intermediate value theorem. This will be the last section that we cover in chapter 4. The intermediate value theorem is an intuitive result with a few surprising applications. I hope you will be surprised. To begin, let's jump right in and state the intermediate value theorem. I'll draw it out first. Here's the idea. Suppose that in my domain I have A and B, and we'll imagine that a function f is continuous on the closed interval from a to b. So I can plug a into my function, I can plug b into the function, and the function is continuous. Now suppose I take any value strictly between f of a and f of b, we'll call it L, and the question is, does there exist some point between a and b that maps onto L? And the intermediate value theorem guarantees that yes, given an L, such a C must exist. Here's the statement. Let f from the closed interval a to b to the real numbers be continuous. If L is any number strictly between f of a and f of b, then there is some point C strictly between a and b where f of c equals L. How about a proof for this thing? This proof will use only two basic ideas, the axiom of completeness and the definition of continuity. So this is a really fundamental theorem. Even though we've seen 4.1 through 4.4, we don't need any of that except for the definition of continuity at a point. For simplicity, we'll assume that f of a is less than f of b, and we'll assume that 0 is some point in the middle. So 0 takes the place of the L that I was looking at previously. I want to show that f of c equals 0 for some c between a and b. First step, let's let k be the set of all those x's between a and b where f of x is less than or equal to 0. So we can see that in the picture here. Whenever my function is negatively valued, or 0, then those x values go into my set k. So if the function value is 0 or negative, x goes into k. X goes into k. Let c be the supremum of k. Now the existence of c is given to us by the axiom of completeness, and c looks like a good candidate for what we're looking for with the intermediate value theorem. We claim that f of c actually equals 0. Now let's bring in the continuity. F is continuous at c, so fix some epsilon greater than 0, and we know there exists some delta greater than 0, such that absolute x minus c less than delta implies absolute f of x minus f of c strictly less than epsilon. I'm going to rephrase that last sentence in a different way that will be very useful to us. It turns out that f of c is strictly between f of x minus epsilon and f of x plus epsilon for all x in the interval c minus delta to c plus delta. That is important enough for the rest of the proof that I will put a blue box around it. Take a second right now if you need to. Pause the video and take a look at these last two lines that are on the slide and make sure you really understand them. Okay, moving on. Since c is the supremum of k, there's some a star just a little bit less than c, or maybe actually equal to c itself, so that a star is in my set k. Now notice, I chose a star to be just a little bit less than c, but still greater than c minus delta. So a star was in that interval c minus delta to c plus delta. Since a star is in there, we know that f of c is less than f of a star plus epsilon. Of course, since a star is in my set k, f of a star is less than or equal to 0. That was by definition of k. And if we put these two sentences together, we find that f of c is strictly less than epsilon. All right. Now, what if I take something a little bit greater than c? Since c is the supremum of k, if a double star is just a little bit more than c, then a double star can't be in my set k. And I'll choose that A star just a little bit more than C, but still within delta of C. Well, since A star is within delta of C, we know, all right, now where do I have it? F of A double star is minus epsilon is less than F of C. Again, using the material in the blue box. Now, since A double star is not in K, I know that F of A double star has to be greater than 0. And once again, I can put these two sentences together and find that negative epsilon is less than F of C. Finally, the last sentence of the proof, I can put these two statements together, and I find that since negative epsilon is less than F of C is less than epsilon for all epsilon greater than 0, the only way this can happen is if F of C actually equals 0, just what we were after the whole time. The textbook has some interesting historical perspective on the intermediate value theorem. The author writes that this theorem was freely used by mathematicians of the 18th century, including Euler and Gauss, without any consideration of its validity. In fact, the first analytic proof was not offered until 1817 by Bolzano in a paper that also contains the first appearance of a somewhat modern definition of continuity. So the appearance of a rigorous definition of continuity really came together hand in hand with this intermediate value theorem. Bolzano and his contemporaries had arrived at a point in the evolution of mathematics where it was becoming increasingly important to firm up the foundations of the subject. There are several satisfying arguments for this simple result, that is the intermediate value theorem, each one isolating in a different way the interplay between continuity and completeness. Those are the key ingredients. I'll show a second proof of the intermediate value theorem in a second, but first, here is a nice corollary to it, the preservation of intervals. We've seen that if K is a compact set, then f of K is also compact when f is continuous. But a continuous function doesn't necessarily preserve open sets, it doesn't preserve closed sets. But here is a nice result. If f is continuous, it does preserve intervals. Let I be an interval. If a function from I to R is continuous, then f of I is also an interval. I can be any kind of interval. It can be bounded, it can be unbounded, it can be open, closed, half closed, it doesn't matter. As long as I is an interval, f of I will also be an interval. We haven't really talked about intervals, but here is the defining characteristic, which should seem self-evident. I is an interval if, whenever I have 2 points A and B in I, then every point between A and B is also in I. So A and B being in I implies that the closed interval from A to B is also in I. That's what makes I an interval. Okay, the proof of the theorem. So let alpha and beta be in f of I with alpha less than beta. So I will draw this down here. Some alpha down there. There's a beta up there. Alpha is less than beta. Let gamma be strictly between alpha and beta. There's gamma. The claim is that gamma is also in f of I. Gamma is the image of some element in I. So see that alpha must be f of x1. There's an x1. And beta must be f of x2. For some x1 and x2 in my I. Oh, incidentally, I'll just draw it as open parentheses there. Let A be the minimum of x1 and x2. So this x2, I'll just go ahead and erase that. We'll call that A. And let B be the maximum. So I'll just call this B over there. All right. By the intermediate value theorem, there exists a C within A and B such that f of C equals gamma. So some C where f of C equals gamma. Oh, well, C must be in I. So A and B are in my interval, and an interval contains everything between it, so C is in my interval as well. And since c is in the interval, f of c is in f of I. So in other words, gamma is in f of I. Which is to say, gamma was just chosen arbitrarily between alpha and beta. That means that every value between alpha and beta is also in f of I. So in fact, the closed interval from alpha to beta is a subset of f of I, and so indeed f of I must be an interval. There it is, a nice corollary to the intermediate value theorem. Intervals are preserved under a continuous function. Here's our second proof. And this one uses the nested interval property. Again, nested interval property, one of those foundational things we looked at the beginning of the course. And again, the same situation. For simplicity, let's assume that f of a is less than f of b, and there's 0 in between. And we'll prove that f of c equals 0 for some c between a and b. So in this proof, let a0 be a, let b0 be b. That's a sub 0 there, b sub 0 there. And let I sub 0 be the closed interval from a0 to b0. Let z be the midpoint of a0 and b0. Now, if f of z is greater than or equal to 0, as it is in the picture, let a1 be a0 and b1 be the z. So here's a little picture maybe to think about it. Given an interval, I'm going to create a subinterval based on what's happening at the midpoint. So if my function is greater than 0, then I'm going to make a new interval that's to the left. And if it happens that my function is less than 0 at the midpoint, then I'm going to take a next interval that's the right half. If f of z is less than 0, then a1 is z, b1 is b0. So I take the right half of the previous interval. Let I1 be a1, b1. So we can continue this process and see how I sub n is defined. And it's not too hard to show that the hypotheses of the nested interval property are satisfied. Closed intervals all nesting in each other forever and ever. So, by the nested interval property, there has to exist some c that's contained in the intersection of everything. What property must c have? Probably f of c equals 0, right? But why is this so? It's because we can consider sequences of left endpoints and sequences of right endpoints and use continuity. And that is actually one of your homework problems. So for homework, focus on these 1, 2, and 3, prove those carefully, and submit that as part of your homework. Okay, moving on. Is the converse of the intermediate value theorem true? In other words, if f is defined on a closed interval from a to b, and if it happens that for all L between f of a and f of b, let's see, f of a, f of b, so there's some a, there's some b. For all L, it happens that there really is some c, so that f of c equals L. Does this imply that f is continuous on the closed interval from a to b? Pause the video, make your guess, and when you think you have your answer, unpause it, and we'll see. The answer is no. Here's an example. I can just draw it right out. Let's imagine that the function breaks at some point. It's discontinuous. But we can see in this picture that any value I pick between f of a and f of b will have some corresponding, maybe even two different values of c, such that f of c equals f of L. Okay. For what it's worth, any function like this that does have this property is said to have the intermediate value property. All right, let's move on to some applications. Intermediate value theorem and roots. Does the function f of x equal x squared minus 37x plus 13 intersect the x-axis within the interval from 0 to 2? Yeah, it does. Let's just take a quick check. F is continuous on 0 to 2 because it's a polynomial. F of 0 is greater than 0. Plug in 0, you get 13. F of 2 is less than 0. I don't even care what F of 2 is, but you can see that if you plug 2 in there, you're going to get a negative number. And so, yep, it works. There must exist some C where F of C equals 0. All right. A slightly more complicated application with roots. Any odd degree polynomial has at least one real root. So we could write f of x equals x to the n plus all these other things where that exponent n is odd. Not getting into too many details here, for some b sufficiently large, it has to be the case that f of b is greater than 0. For some a sufficiently large and negative, f of a will be less than 0, and this has to do with the properties that the largest power is going to overpower everything else eventually, and that power evaluated at a positive number is positive, this power evaluated at a negative number is negative, and so consequently there's some c in the interval from a to b such that f of c equals 0. There has to be a root. The monk's trip. This is a great problem. A Tibetan monk leaves the monastery at 7 a.m. and takes his usual path to the top of the mountain, arriving at 7 p.m. Along the way, he occasionally stops and rests, and even backtracks at times to help fellow travelers. The following morning, he starts at 7 a.m. at the top and takes the same path back, occasionally resting, and arrives back at the monastery at 7 p.m. Here's the claim. There is a point on the path that the monk will cross at exactly the same time of day on both days. Again, pause the video, see if you can reason out why this is so, and then start when you're ready. Here's how I approach it. Let's make a graph, and we'll graph the distance from the monastery. He starts at the monastery and goes to the mountain. The distance from the monastery as a function of time. So he starts at the monastery, travels, he's going up the mountain. He might rest for a little while, which is indicated by a flat section. He might backtrack for a while, he goes down, but eventually he makes his way, after 12 hours, to the top of the mountain. So we'll say capital M, that's the total distance it takes for him to get to the mountain from the monastery. Now let's graph his travels on the second day, from the top of the mountain back down to the monastery. In this case, he starts at the top, and he'll travel down, maybe he'll rest for a little while, continue down, and eventually he comes back to the monastery. Let's label these two functions. We'll say his trip up the mountain is f of x, and his trip down the mountain is g of x. These are continuous functions. Our monk is not a magic monk. He cannot disappear in one place and reappear in another place instantly. And so what will the function f of x minus g of x look like? F minus g, well, it starts at negative m, and over the course of 12 hours, it will end at positive m, and the function is continuous. So there must be some point c where f minus g crosses the x-axis. So in other words, at this point c, I guess I didn't draw my picture really appropriately, c is going to be this point. So c is the time that the monk crosses exactly the same point on the path on both days. Here's almost an identical problem, just phrased in terms of rigorous mathematics. Suppose f and g are continuous on 0 to 1. F of 0 is 0 and f of 1 is 1. And g starts at 0 and g ends at 1. G is continuous. Does there exist c so that f of c equals g of c? And yes, there does. We can prove this rigorously. Say let h of x equal f of x minus g of x. H is continuous on the interval from 0 to 1. H of 0 equals negative 1. H of 1 equals positive 1. By the intermediate value theorem, there must exist some c strictly between 0 and 1 such that h of c equals 0. Well, h of c equals 0 tells me that f of c equals g of c. And that's it. This is a great application. Jogging around town. Beth takes her usual 1-hour jog around town, starting and ending at her house. In the center of town there is a bell tower, and her jog takes her around the bell tower. Claim. There are 2 points along her route that are exactly opposite the bell tower and equidistant from the bell tower. Pause the video for a second, and when you think you can reason this out, start the video up again. Let's imagine that she jogs counterclockwise, and for any point x on the path, I'm going to say f of x is the distance from that point on the path to the bell tower, and we'll say g of x is the distance opposite the bell tower to the corresponding opposite point on her path. And it's believable that f of x and g of x are continuous functions. Well, let's actually give this a specific point. Let's say this is x1 and g of x1 there. And in the picture, it's clear that f of x1 is less than g of x1. Well, what will happen as she moves from x1 around until eventually she gets to the opposite point? And we'll call that x2. Well, now f of x2 is the distance to the bell tower, and g of x2 is that opposite side distance. We can see that f minus g of x1 is negative, whereas f minus g of x2 is positive. Thus, there must be some value c where f minus g of c actually equals 0, so f of c equals g of c. And that's it. So, I don't know, in this picture, maybe what looks like it could work. Something like that. Is this my point C? Alright, one last application. Here's our last curious fact that comes as a result of the intermediate value theorem. Suppose f from 0 to 1 to r is continuous with f of 0 equals f of 1. Now, I'll draw f of 0 and f of 1 both actually equal to 0, but that's okay. Anything works. Show that there are 2 points, x and y, such that f of x equals f of y, and y minus x equals 1/2. So maybe, I don't know, as I look at this, maybe something like that works, where I have x and y, and the horizontal distance between x and y is 1/2. So y minus x is 1/2, f of x equals f of y. How can we find this? If you think you can work it out, pause the video for a second and give it a try, and when you're ready, unpause and I will explain. Here we go. Here's the trick. Let g of x equal f of x minus f of x plus 1/2. So I'm basically taking the same graph and just shifting it to the left by half a unit. I'm going to see which points line up, and by subtracting it, I'm going to figure out where is my g of x equal to 0. So g is continuous on 0 to 1/2. Watch your domain. G of 0 is f of 0 minus f of 1/2, and g of 1/2 is f of 1/2 minus f of 1, and the key observation is that f of 0 and f of 1 are the same. In fact, in my picture I made them both equal to 0, and so it's evident that g of 0 is negative g of 1/2. They are opposites, so one is positive and one is negative, or they're both 0. In either case, we find that there must be some c in the interval from 0 to 1/2, such that g of c equals 0. Taking it back to f, that means that f of c, I'll call that c my x, is equal to f of c plus 1/2, there's my y, as needed. Interestingly, the same problem doesn't work if instead of using 1/2 I try something like 3/4, because you can draw a little example showing a graph like that, 0 to 1. There's no length of 3/4 that you can draw between 2 points on that graph. And that brings us to the homework. A mercifully short homework assignment this time. Try problems 2, 5b, and 7. As a bonus problem, try problem 6c. It asks for an example. You can just give an example by drawing carefully. You don't have to make a function or a formula like sine of x. Just give me a really nice drawing. All right, that's it. Good luck. Ask me as you have questions.